Hello everyone, I'm Xinglei. I will present our work, OSML, Intelligent Resource Scheduling for Co-located Latency Critical Services, a multimodal collaborative learning approach. Resource contention may occur when multiple applications are co-located on a server. Runtime resource scheduling is the pivot for QoS control in these complicated co-location cases. Scheduling co-located services faces several challenges. First, co-located services exhibit diverse behaviors across the storage hierarchy. Second, the enlarging scheduling exploration space and multiple interactive resources make it hard for schedulers to provide ideal solutions quickly and efficiently. Third, we observe the resource cliff phenomenon of latency critical services. That is, decreasing a resource only slightly during scheduling can lead to a significant QoS slowdown. This phenomenon reduces the exploration efficiency and leads to severe QoS fluctuations. To address these challenges, we design OSML, a multimodal collaborative learning-based resource scheduling approach. OSML can achieve higher loads and take less time to meet QoS targets compared with prior work. Cloud applications are shifting from monolithic architectures to loosely coupled designs, including many LC services with strict QoS requirements. Multiple services are often scheduled on one server simultaneously to increase server utilization and cost efficiency. These co-located services exhibit diverse behaviors across the storage hierarchy, including multiple interactive resources such as CPU cores, LLC, memory bandwidth, I/O bandwidth, and main memory banks. These co-located services contend for shared resources, leading to QoS violations of LC services. LC services have strict QoS targets. Violating the QoS targets often leads to financial loss. Many prior studies have been working on mitigating QoS violations. However, they still have room for improvement in scheduling convergence time, intelligence, and how to schedule complicated interactive resources in a timely fashion. Moreover, existing schedulers cannot easily avoid the resource cliffs. They often incur unpredictable latency spiking during scheduling. Our community has been expecting new directions on developing resource scheduling mechanisms. We designed OSML, a novel machine learning-based resource scheduler for latency-critical services. To this end, we study resource scheduling for representative latency-critical services. This figure shows the resource scheduling exploration space of MOSES. In this figure, each cell denotes the response latency of MOSES under a specific number of cores and LLC ways. We have two key observations. The first is the resource cliff. We call it RCliff hereafter. The RCliff is highlighted using red line in this figure. RCliff is defined as the resource allocation cases that could incur the most significant performance slowdown if resources are deprived via a fine-grained way in the scheduling exploration space. RCliff alerts the scheduler not to allocate resources close to it because it is dangerous to fall off the cliff. The second is the optimal allocation area, which we call OAA. OAA denotes the ideal number of allocated cores and LLC ways that can bring an acceptable QoS. OAA is a goal that the schedulers should achieve. We investigate many commonly used services. We find the RCliff always exists. We also show that OAA is not sensitive to the number of concurrent threads. In front of OAA and the RCliff, we find three main shortcomings in the existing schedulers. The first is that the existing schedulers are entangling with RCliffs. The figure below shows an example. If the current resource allocation for an LC service is in the yellow color area in this figure, the scheduler has to try to achieve OAA. However, as the scheduler doesn't know the location of OAA, it has to increase the resource step by step in a fine-grained way. Thus, the entire scheduling process will incur very high response latency. For another example, if the current resource allocation is close to RCliff, a slight resource reduction for any purpose has the danger of falling off the RCliff, leading to a sudden and sharp performance drop. The second issue is that existing schedulers are difficult to accurately and simultaneously schedule a combination of multiple interactive resources to achieve OAA in low overheads. The third issue is that existing schedulers are difficult to provide accurate QoS predictions. They can hardly balance the QoS and the resource allocations. More details can be found in our paper. An ideal scheduler should avoid RCliff and quickly achieve OAA from any positions in the scheduling space. We claim it's time to design a new scheduler, and use machine learning can be a good approach. We propose OSML. OSML is a data-driven approach based on a dataset collected from 11 typical LC services shown in the table below. The dataset covers around 62 million resource allocation cases and around 2 billion samples. Details on data collections can be found in our paper. OSML uses collaborative machine learning models for intelligent resource scheduling. Model A and Model B are data-driven static models. OSML uses Model A to predict OAA and RCliff. Model B is used to balance QoS and resource allocations among collocated LC services. Model C is a reinforcement learning model. It is used to handle the changes on the fly. Moreover, OSML is designed as a co-worker of the OS scheduler. It is located between OS kernel and the user layer. This slide summarizes all models used in OSML, including Model A shadow, Model B shadow, and Model C. The two shadow models are designed to handle different scenarios in practice. The features listed in this table are used as inputs of the models. The third column of the table shows which models each feature is used for. The second table characterizes the models. Now, I will introduce each model individually. Model A predicts RCliff, OA, and OA bandwidth. Model A has 9 input features. The output tuple items include RCliff cores, RCliff LC width, OA cores, OA LC width, and the memory bandwidth requirement of OA. Model A has a shadow. It provides solutions when multiple LC services are collocated. Compared with Model A shadow has the same outputs but has 3 more input features related to neighboring applications. Model B balances the QoS and the resource allocations among collocated LC services. It predicts resources that a service can be deprived of and the allowable QoS slowdown. Model B outputs 3 policies, as the computing units and memory resource can be fungible. The term cores dominated indicates a policy using more cores to treat the LC width and vice versa. Model B shadow predicts QoS slowdown if a certain amount of resources is deprived of a specific service. Compared with Model A shadow, Model B shadow has 2 more input features related to the resources after deprivation. Model C is a reinforcement learning model based on DQN. It shepherds the allocations and recovers from QoS violation and resource overprovision cases. Model C has 8 input features. The scheduling actions are defined as the action function here, in which a positive M denotes allocating M cores for an application, and a negative M means depriving it of M cores. N indicates the actions on LC width. The reward function is defined as follows. It has 2 parts. The blue part gives higher reward to actions that bring lower latency. It mitigates QoS violations. The red part gives higher reward to actions that bring less resource usage. This figure shows OSML's central logic. The collaborative machine learning models are used in OSML in a pipeline way. Algorithm 1 shows how OSML allocates resources for a newly coming LC service in practice. The central controller enables Model A or Model A shadow to get the OA and RCliff. If idle resources are sufficient to satisfy the new LC service, then allocate resources to the service. If not, enable Model B to deprive resources from neighbors and allocate them to the new one. If the resources are still not sufficient, the scheduler enables resource sharing by calling Algorithm 4. Algorithm 2 handles resource overprovision cases. When the scheduler detects QoS violations, Algorithm 2 calls Model C to allocate more resources to achieve ideal QoS. If idle resources are not enough, call algorithm 4 for resource sharing. Algorithm 3 handles resource over-provision cases. It calls Model C to reclaim over-provisioned resources. If QoS is not satisfied after the deprivation, the action is withdrawn. Algorithm 4 handles resource sharing among applications. It enables Model B shadow to predict QoS slowdown after resource sharing. If the slowdown is acceptable, share a resource with neighbor. If not, migrate the application. We evaluate OSML on a platform with Intel Xeon E5 CPU, which has 36 logic cores, 45 MB LLC, and 20 LLC weights. OSML captures traces using PQS and PMU. The CPU, LLC weights, and memory bandwidth are managed using Linux task set, Intel cache allocation technology, and Intel memory bandwidth allocation. We use the similar metrics as prior work. The first is QoS, quality of service. We set the QoS target for each LC service as a 99th percentile latency at the knee of the latency to RPS curve. The second is EMU, effective machine utilization. It means the maximum aggregated load of all collocated LC services. We compare OSML against 4 competing technologies. Parties, a heuristic-based scheduling approach. CLite, a scheduler based on Bayesian optimizer. A managed allocation. For Oracle, it uses the best allocation policy obtained by exhaustive offline sampling. Firstly, OSML exhibits a shorter scheduling convergence time. Figure A shows the performance distribution for 104 loads that OSML and other baselines can all converge. Figure B shows the violin plot of convergence time for these loads. We can see from the average convergence time that OSML converges faster than the baseline approaches. Generally, OSML can achieve the same EMU with a shorter convergence time for a specific load. OSML converges faster mainly because the start point provided by Model A is close to OAA. We also show that OSML works for more loads across different EMUs, particularly in cases where the EMU is high. OSML uses fewer resources to support the same loads to meet the QoS targets. This figure shows the actions used in OSML and other baseline scheduling process for case A. This figure highlights the scheduling actions using solid red lines to represent increasing resources, and blue dotted lines to denote reducing resources. We observe that OSML has the least resource usage. It saves 3 cores and 9 LLC weights, while other baselines use all resources on the platform. OSML provides solutions for sharing some cores and LLC weights among LC services, therefore supporting higher loads. For example, in this figure, OSML can support this load by sharing 2 cores between 2 LC services. The baselines cannot converge for this load. Another figure shows the achieved loads of a combination of 3 LC services. OSML can achieve 10% to 50% higher loads in the highlighted cells in figure D. We evaluate how OSML behaves with dynamically changing loads. As illustrated in figure A, in the beginning, 3 LC services arrive into. We observe the response latency increases caused by the resource contention among them. OSML provides better scheduling solutions at time point 48 for all 3 services. From time point 180 to time point 228, we increase the load for ImageDN as illustrated in figure A. This figure highlights the scheduling action for OSML and other baselines. OSML's Model C can handle QoS violations of ImageDN even the load increases. We also evaluate OSML using all NC applications. OSML performs well, showing good generalization performance. The model errors are not significant, even for new applications or platforms. Model A and Model B can still output the approximate OAA. Model C handles the errors as it learns online. More importantly, OSML is a long-term project open to the community. We continue adding new traces collected from new applications and new servers to the dataset for enhancing models' performance for new cases. In this work, we present OSML, a machine learning-based resource scheduler for co-located LC services. OSML uses multiple machine learning models cooperatively in a pipelined way. More importantly, we advocate leveraging machine learning to enhance resource scheduling. This could have an immense potential for OS design. In a world where co-location and sharing are a fundamental reality, our solution should grow in importance and benefit our community. Thank you. If you have any questions, please feel free to ask.